Biochemist Rana is Vice President of Research and Apologetics at Reasons to Believe. He pursued postdoctoral studies in the biophysics of cell membranes at the universities of Virginia and Georgia. Though he initially embraced the evolutionary paradigm, Fuzz eventually drew the conclusion that only a creator's involvement could explain the elegance of biochemical systems. Please welcome Fuzz Rana.
Well, good morning, everybody. My question for you to get things rolling is, why are you here this morning? Do you want to know why I'm here? Biochemistry. That's why I'm here. And I'm not talking about the metabolic reactions that are happening inside each of the cells of my body that make my existence possible. And by the way, those reactions are happening inside the cells of your body too. But rather, I'm talking about the discipline of biochemistry. And for those of you who don't know what biochemistry entails, it's the area of science where the goal is to understand life at a molecular level, at its most basic foundational level. Biochemists are all about identifying the molecules that make up living systems. How are these molecules structured? How do they react with each other? And how does that structure and function activity relate to higher order biological processes that are necessary for life? Again, biochemistry is about understanding life at its most basic fundamental level. And I can't think of a more exciting area in science than biochemistry. And I also can't think of a more exciting area when it comes to scientific apologetics, that is, using science as a way to defend the Christian faith, than biochemistry. In fact, biochemistry paved the way for my conversion to Christianity. I was an agnostic when I entered college. I didn't know if God existed or not, and I really didn't care. Now, if you ask me, did I think God existed, I very well could have said yes. I grew up in the Bible Belt in West Virginia, and it was fashionable at that time to acknowledge or to give a nod to the possibility of God's existence. But in my heart of hearts, I didn't really know, and I didn't really care. What I was focused on as a college student was preparing myself to go to graduate school to become a biochemist. I was a nerd, I admit it. So I took courses in chemistry and in biology and in physics. And in my biology courses, the professors that I deeply admired and admire to this day taught that life's origin and life's history could be explained through evolutionary means. And I accepted those ideas. In fact, those ideas fueled my agnosticism, because if evolution can explain the origin and the history of life, then you don't need God. Why is God necessary? Why is a creator necessary? In fact, just about a week or so ago, I did a debate with atheist P.Z. Myers on Darwin Day at North Dakota State University. Yes, it was very cold, outside at least, and it was hot in the auditorium. But one of P.Z. Myers' points, and I hear this from atheists who are in the sciences, that again, if evolution can explain life's origin and life's history, why is a creator necessary? I encounter so many people who've gone through biology classes where that message is communicated, and they, again, reach that same conclusion, that if evolution can explain everything, why do you need a creator? Have you ever encountered somebody like that? What do you say to them? How do you address that concern? That's what we're going to be talking about in this session. Now, for me, it was biochemistry that dislodged me from my agnosticism. Because when I went to graduate school, I now was studying biochemistry at the cutting edge. I was immersed in biochemistry on a day-in, day-out basis. I was taking advanced courses. I was beginning to do my own research. I was reading the scientific literature. I was interacting with students and professors, and I very quickly came to the recognition that biochemical systems are complex. But it wasn't the complexity that impressed me. It was the elegance of these systems. It was the ingenuity of these systems, the sophistication, the beauty. Yes, there's beauty in science, as there is in art, in literature. And I asked myself, how do scientists explain where these systems come from? I didn't want a hand-waving explanation, evolution did it. I wanted to know the details. And I began to study this question. How do we explain the origin of biochemical systems? This is called the origin of life problem. And I quickly came to the conviction that chemistry and physics alone could not generate the types of systems that you see in the cell. There has to be a mind that undergirds life, that brought life into existence. It was at that point I came to the recognition there had to be a creator. And once I became convinced that a creator existed, I was now open to the gospel. When I was an undergraduate student, I had friends who were Christians, and they would share their faith with me. And I would think to myself, this is the most ridiculous thing I've ever heard in my life. I liked these people. They were my friends. I felt sorry for them. But then when I came to the recognition a creator existed, those crazy ideas that they were telling me about suddenly became ideas that I apprehended, and I responded to the truth of the gospel. And the exciting thing, for me at least, maybe not for you, but for me the exciting thing is the very lines of reasoning that led me to conclude a creator must exist almost 30 years ago now. I know I look much younger than that. But those same lines of evidence are the same types of evidence we can marshal today to make a case for a creator's existence, at least from biochemistry. And to summarize these lines of reasoning, just think of the 3 F's. F's aren't a good thing in school, but they're a great thing this morning. And those 3 F's are fingerprint, failure, and fashion. That when we look at biochemical systems, we see powerful evidence for God's fingerprints in these systems. Any attempt to try to generate and explain the origin of life and the origin of biochemical systems through evolution leads to failure, and attempts to create life in the laboratory or to fashion life demonstrates unequivocally the role intelligent agency must play in bringing about life. So let's go ahead and take a look at the first argument. God's fingerprints are evident in the record of nature. One of the things that I find really provocative as a biochemist is this, that the defining features of biochemical systems are identical to those features that we would recognize as evidence for the work of a human designer. Let me say it another way. When human beings design, when we create, when we invent systems and devices and objects, those things we produce have certain properties that reflect the work of a mind. And when we look at biochemical systems, they have those same properties as well. These are the defining properties of biochemical systems. So by analogy, if these features reflect the work of a human mind and we see the same features in the cell, is this not evidence for the work of a divine mind? Let me illustrate this by talking about the information systems in the cell. Now, our common experience is information comes from a mind. If you drive through the Hollywood Hills and you see the big Hollywood sign, what do you conclude about where that sign came from? It came from a mind, did it not? And this is true no matter where we encounter information. It always, in our experience, comes from a mind. And it's provocative in light of that to note that at their very essence, biochemical systems are information systems. The 2 most prominent classes of biomolecules that are information-harboring molecules are DNA and the proteins. And these molecules harbor information in their very structure. That in and of itself suggests the work of a mind, but the argument is much deeper than that. For example, information theorists who study molecular biology have come to recognize that the way in which biochemical systems are organized in terms of their information content is identical to the way that we would organize language. That biochemical information is organized in the form of a language, a biochemical language that is analogous to how we organize information in languages. So it's not the mere presence of information, it's how it's organized, it's how it's structured. It's structured and organized the same way that we do it. Something that's even more remarkable is the recognition in recent years that the cell's machinery that manipulates DNA, which again is an information storage molecule, functions fundamentally in the same way a computer system functions. This is a type of insight that keeps me from sleeping at night as I think about the implications of this. And that's my challenge to you, is think about the implications of this, not just for the next few minutes, but mull this over, because I'm still working through the implications. They're so profound. And this is worth spending a little bit of time unpacking. So I'm going to get a little technical here, but I think it's well worth it. And to appreciate why biochemical systems, again, are built like computer systems, we need to think about the work of Alan Turing, the British mathematician. Now, about a year ago, nobody would have known who Alan Turing was. But thanks to the movie The Imitation Game, most people now have an idea who Alan Turing was. A British mathematician who's the father of computer science. But in the movie The Imitation Game, how many of you saw the movie, by the way? It's a great movie. I highly recommend it. In that movie, the focus is on Turing's role in cracking the German Enigma code in World War II. And to do this, he built the very first computer system. And the computer system he built was based on theoretical work he did prior to World War II. That theoretical work forms the foundation for computer science today. And the core of Turing's theoretical ideas were something dubbed a Turing machine, which is an abstract machine that exists only in Turing's mind that consists of three parts: an input, an output, and a finite control. And here's a cartoon showing a Turing machine. The input is a string of data, information, that goes into a machine called a finite control that alters that data and produces an output. And Turing's genius was to realize that while that finite control could only do very limited transformations of the data, if the output is married to the input of another Turing machine, and you do that over and over again, you can take very simple operations and perform very complex computations. And that, in fact, is what Turing did when he built the very first computer. It was essentially a bank of Turing machines where the input and the outputs were linked together. Now let's take a look at a process that's critical to life: DNA replication. The information in DNA has to be replicated to be transmitted to the next generation. If you want to have reproduction, you got to have DNA replication. And it's information. And these little balls and donuts and blobs that are here are depicting components of the cell's machinery that are, in effect, Turing machines that take the DNA input, alter it, produce an output that another machine takes as input and generates an output. This is literally a computer operation when DNA is replicated, where, again, the DNA is the input and the output, and the cell's machinery that's operating on the DNA is the finite control. This analogy is so stark that it's given rise to an entire new area of nanotechnology called DNA computing. And the father of DNA computing is Leonard Adleman, a scientist at the University of Southern California. And based on his pioneering work, there are now technologists that are looking to build computers out of DNA and the cell's machinery that manipulates DNA. And these computers are found in test tubes that are that big. And they're more powerful than the most powerful supercomputer system that we've built today. This is the frontier for computer science. This is what Leonard Adleman said in an interview. The most important thing about DNA computing is that it shows that DNA molecules can do what we normally think only computers can do. This implies that computer science and biology are closely related, that every living thing can be thought to be computing something, and that sometimes we can understand living things better by looking at them as computers. This brings to mind the watchmaker argument. William Paley, the British natural theologian in the late 1700s, in a book called Natural Theology, advanced the watchmaker argument, which basically is a watch requires a watchmaker, life requires a creator. In Paley's day, the pinnacle of engineering achievement was a watch. And Paley noted that a watch has certain properties that reflect the work of a mind, and when he compared a watch to biological systems, he saw a machine-like nature to them, like a watch, and concluded that if a watch requires a watchmaker, there must be a divine watchmaker. Now think about this. Who in their right mind would say that a computer system emerges through undirected evolutionary processes? Computer systems, which are the pinnacle of our engineering achievement, come from minds, ultimately from Alan Turing's mind. And so when we take off the cover of the cell and we look at the machinery in the cell and we see that it's functioning like a computer system, it's at least minimally reasonable to think that it came from the work of a mind, is it not? If you want more information about how this argument for design works, revitalizing the watchmaker argument, I recommend my book to you, The Cell's Design. Now, when you make an argument like this, the rebuttal is going to be basically this. Of course, these systems that we see inside the cell are elegantly designed. Nobody disputes that. And yes, indeed, there is a watchmaker, but that watchmaker is not a person. It's the blind evolutionary forces. It's the blind watchmaker. This is how Richard Dawkins describes the blind watchmaker. Paley had a proper reverence for the complexity of the living world, and he saw that it demands a very special kind of explanation. The only thing he got wrong was the explanation itself. The true explanation had to wait for Charles Darwin. Which leads us to the second point, and that is every attempt to try to explain the origin of biochemical systems through a blind watchmaker approach of evolution have led to failure. So that's our second F, failure. Now, to appreciate this, we need to spend a little bit of time talking about some biochemistry basics, just for a few minutes. When biochemists look at the cell, they note that there are three main features of biochemical systems. One are the information harboring molecules like DNA and RNA and proteins. We talked about those. There's another collection of processes happening in the cell called intermediary metabolism. That's a mouthful, and when you take a biochemistry course and you have to learn about intermediary metabolism, it is a nightmare. Because inside the cell, there are thousands of small molecules that react with each other, and these reactions are organized in linear and branch pathways and cycles, and they all they interact with each other and interconnect to form this highly reticulated network of chemical reactions that are extremely well organized. This is called intermediary metabolism, and this is very important. Did any of you have a muffin during the break? Well, if you had a muffin, you basically consumed a sugar bomb. And that sugar that goes into your stomach gets digested. So the sucrose, it's broken down into glucose and fructose and is absorbed by cells. And then there's a metabolic pathway called glycolysis that converts those molecules into smaller molecules, breaking them down. And then those small molecules are swept into something called the Krebs cycle, and that process is good because it generates compounds that can be used by the cell to power the cell's operation. It's a source of energy, so it's good. But if you happen to have two muffins or a muffin in one of those apple turnovers that I had this morning, you probably consumed too much glucose and fructose to burn off, so these same metabolic pathways are going to generate fats with that excess energy. And that's good because it stores that energy for later use, but it's also good because those fats serve as building blocks to make cell membranes. And so these pathways are not only harvesting energy, they're providing building blocks for the cell. And that leads us to the third system, and that is the membrane, which is the boundary that separates the interior of the cell from the exterior environment. Now, these three different features of life's chemistry have led to three different approaches for the origin of life, called the replicator first, metabolism first, and membrane first scenarios. Replicator first scenarios are this idea that the information molecules arose first and then everything else followed. Metabolism first scenarios are that metabolism emerged first and then everything else followed. And then membrane first scenarios are that the membranes emerged first and everything else followed. But all three approaches lead to dead ends. The problems with the replicator first scenario are legion. And I'm not going to get into the details of these problems this morning. I'm just going to simply say that this approach has led to a dead end. In 2002, in the summer of 2002, Hugh Ross and I traveled to Oaxaca, Mexico to attend an Origin of Life conference called ISIL 2002. The ISIL conferences are held every 3 years. They attract the premier Origin of Life researchers from around the world. And we were working on a book called Origins of Life, and we wanted to go to the conference to complete our research for the book, because we're going to get the cutting edge information at that time on Origin of Life research. And the opening plenary lecture was given by a guy named Leslie Orgel, who when he was alive was considered the godfather in the Origin of Life research community. He was the big kahuna. And he was invited to give the opening plenary talk on replicator first scenarios, because he's the father of a very important scenario called the RNA world scenario. And he delineates problem after problem after problem in this opening lecture. And towards the end, he pauses and he says this: I sure hope there are no creationists in the audience, but it would be a miracle if a strand of RNA ever appeared on the primitive Earth. Think about that for a minute. Leslie Orgel is an atheist, committed his entire research career to understanding the origin of life, and his parting words are that replicator first scenarios might as well appeal to a miracle. The problem is metabolism first scenarios don't fare much better. Orgel, in an article that he wrote right before he died, said this with regard to metabolism first scenarios: they would require an appeal to magic, a series of remarkable coincidences, a near miracle. When it comes to membrane first scenarios, these also don't work. In fact, this is where I had an opportunity to make a contribution to this whole problem. A few years ago, a chemist named Jackie Thomas and I wrote a critical review of membrane first scenarios and had it published in the premier Origin of Life journal called Origins of Life and Evolution of Biospheres. And this was peer review work where we summarized all the problems with membrane first scenarios, and it was published in a peer reviewed journal where the reviewers acknowledged our criticism of this approach to the origin of life is valid. The bottom line is every attempt to explain the origin of life through a blind watchmaker approach leads to failure. If you want more information, the book Origins of Life may be of interest. Now, what happens when you make that kind of an argument to people that know something about the origin of life? They agree, but then they'll say this: what about all the success we've had in the laboratory identifying different chemical and physical processes that could contribute to chemical evolution? Origin of life researchers cannot go back in time and observe what happened when life originates. So what do they do? They go in the lab and they try to recapitulate different steps in the origin of life. And in the process, they are literally trying to create life in the laboratory following the steps that they think chemical evolution took. And when you look at the literature over the last 60 years, there's remarkable success that they've achieved in terms of identifying processes that in principle could contribute to the origin of life. But the irony is that this is false success. That instead of demonstrating the validity of chemical evolution, it ironically supports the notion of intelligent design. And that brings us to the third point. Attempts to create life in the lab demonstrate the role intelligence must play in creating life. Why is that? Because in the laboratory, researchers are able to do some really neat things. They can assemble a glass apparatus, they can create starting conditions, they can control concentrations, they can exclude contaminating materials that would interfere with the reactions, they can stop the reaction at the just right time, they control the order of addition. In other words, they rig the setup so that the chemistry is successful. That is, their role as an intelligent agent has influenced the outcome of the experiment. And the big difference between the lab and the early Earth is the presence of organic chemists in the lab and the absence of organic chemists on the early Earth. Because as soon as you try to take that chemistry from the lab and translate it to the conditions of the early Earth, it becomes unproductive. Let me illustrate this very quickly with what's called the RNA world scenario. And I'm not going to get into the details of this, other than to say this is an idea that the very first life forms were built around RNA molecules, and that the RNA world later evolved to give rise to the DNA protein world. And there's a number of different lines of evidence people will point to for the RNA world scenario. One of them is the ability of RNA to assemble on clay surfaces from RNA building blocks. And I remember when this work was published, it was heralded as a grand achievement when it came to origin of life research. And the idea here is that if the RNA building blocks were present on the early Earth, they could absorb onto mineral surfaces that would then function as catalysts to drive the formation of RNA. And once you have RNA, the RNA world kicks in. The problem is when you examine the work that's been done to show RNA assembly on clay surfaces, you quickly see the role intelligent agency has to play. These experiments are set up to very carefully exclude interfering materials that would either prevent the RNA growth or cause the RNA to break down. And these materials that are eliminated would be present on the early Earth at very high levels, meaning you're never going to get out of the chute with an RNA world. In addition to that, the researchers stop the reaction before the RNA chains get too long, because when they get too long, they irreversibly bind to the clay and they don't come off. And when that happens, those RNA molecules are out of the game. You don't have an organic chemist on the early Earth stopping the chain growth, assuming it happens. But you do in the laboratory. And then finally, to get the experiment to work, you've got to buy the clay from a very specific supplier. The clay has to then be treated in the lab, and then you have to get building block materials that you chemically modify so that they become more reactive. Again, all these processes aren't going to happen on the early Earth, but they can happen in the lab. In other words, the researchers have played a critical role in the success. This is what Paul Davies, an astrobiologist and a physicist, has said about this problem. As far as biochemists can see, it's a long and difficult road to produce efficient replicators from scratch. This conclusion has to be that without a trained organic chemist on hand to supervise, nature would be struggling to make RNA from a dilute soup under any plausible prebiotic conditions. Simon Conway-Morris goes one step further. Many of the experiments designed to explain one or other step in the origin of life are either of tenuous relevance to any believable prebiotic setting or involve an experimental rig in which the hand of the researcher becomes, for all intents and purposes, the hand of God. Any attempt to try to create life in the lab demonstrates the central role of intelligent agency. If you want more on this, my book, Creating Life in the Lab, would be a great place to start. So what have we said? That when we look at the chemical systems inside the cell, we see evidence for God's fingerprints, and we can go beyond merely the intuition of design, and we can actually construct a formal argument for God's existence following after William Paley. That attempts to try to explain the elegant designs of biochemistry through chemical evolution, through a blind watchmaker approach, have led to failure, and these very experiments demonstrate that intelligent agency is critical to bringing life into existence. And I would submit to you that this is a very powerful argument that you can utilize when somebody says to you, God isn't necessary because evolution can explain the origin of life. This is a great argument, in my opinion, to use. And once you can again show somebody that a creator exists, it opens them up to asking questions. Who is that creator? How do I relate to that creator? And this is where the gospel presentation can become meaningful. Anyway, thank you so much for your attention.